So it's my pleasure to introduce our next speaker, who is Angela Dai. She's a junior research group leader at the Technical University of Munich, where she leads the 3D Understanding Group. Her research focuses on understanding how the 3D world around us can be modeled and semantically understood. She received her PhD in computer science from Stanford in 2018, and her bachelor's in computer science from Princeton in 2013. Her research has been recognized through a CEDB Junior Research Group Award and an ACM SIGGRAPH Outstanding Doctoral Dissertation Honorable Mention, as well as a Stanford Graduate Fellowship. And yeah, I'm very much looking forward to her talk.
Thanks, Torsten, for the nice introduction, and I hope I can follow up on this this talk that you've just gave. So today, I would like to talk a bit about understanding 3D scans. So I know this is largely a workshop that's based on localization, although I do think there are some pretty significant ties between localization and scene understanding. So I'm a person who's very bad at this human task of self-localization, and I get lost very easily, but I do believe that there is some evidence that higher level kind of semantics of objects, scenes, even more abstract than that, are important towards this task of localization and recognizing, you know, where we are actually in the environments. And I'd like to take a little bit of a deeper look at this particular kind of semantic understanding of scenes. So in particular, I'll be taking a look at the example kind of 3D scans. So here we have observations of RGBD video that have been reconstructed into the underlying 3D geometry that's been observed here. And I think one thing that is particularly interesting to be exploited in this particular domain is trying to tie together some of the work that's been done on the 2D color image domain only to this kind of geometric structure that's underlying many of these environments. So in this regard, I'd like to take a look specifically at these tasks of semantic segmentation, semantic instance segmentation that are directly analogous to these particular tasks in 2D. So here we're looking at, for every point in 3D space, we want to identify which class category it belongs to. And for instance segmentation, we also want to identify which particular object instance that it belongs to. And so here we want to take a look really at how to kind of combine together these multimodal observations from color as well as from geometry. So let's first take a look at the semantic segmentation task. I think, so here we have the inputs as a set of RGB images and the reconstructed geometry. So how we want to actually combine these two together is to first extract semantic features from the color RGB inputs while actually spatially downsampling, so the color inputs. So because when we capture these kinds of RGB plus depth information, usually the RGB is captured at a higher resolution and sometimes a much higher resolution than the geometry. Because the depth is largely inferred from this kind of signal. So we want to compensate for these differences in resolution of the signal by basically spatially downsampling the color input while extracting semantic features, and then back project them actually into 3D space. So then we can now combine them with the geometry input. And so that lets us basically combine together the signal from the color as well as the geometry in order to get final predictions in 3D in terms of class labels in the scenes. And so here, what's interesting to take a look at is basically this kind of multimodality. So what happens if we take a look at the color signal only, or the geometry signal only, and when we combine them together, because intuitively they should be relatively complementary. And here we can see that actually in terms of the average class accuracy over a 20 class task. In geometry, you have actually a nice kind of separation of a lot of objects because there's a physical separation. But it can be very difficult to distinguish between some things like doors and windows and pictures and stuff like this that are actually very, they basically fall into the walls or the other support structures that are there. So this is actually what color actually can help us a lot with in this regard, as well as this kind of higher resolution detail that we can extract from the color signal. So when we combine them together in this way, by extracting semantic features from 2D convolutions on the color images, we can actually get a much better performance by combining together these modes here. And we can also see here, if we take a look at adding in more and more views from the color images, we can actually get better performance. And so the marginal benefit of more and more views does decrease at some point, because at some point you do have a lot of redundancy between the number of views. So here we go up to 5 views, but you see that basically the difference between no color and 1 view is the largest difference in performance here. And as we add in more views, we get more coverage, but at some point that becomes also relatively redundant coverage here. So we end up having this this help in terms of this multi-view incorporation here. And now we can see, you know, kind of the visual results of this kind of approach here. And these are in comparison to previous, like, largely geometry-only approaches. So the noticeable differences here, the black and the ground truth images is actually just because the data hadn't been annotated at that point. But the notable difference here is basically it's like sharper edges that we can get from the color, and also classes like doors and windows and stuff like this. This we can get with much more reliable accuracy when we combine together both the color and the geometry signal. The doors in red and these pictures in brown that you can see are very difficult to determine from only color kind of, or sorry, only geometry input. And so this lets us get to a nice way to combine together color and geometry in terms of semantic segmentation. I mean, in practice, we do also want to be able to determine not only the class category for these points in a scene, but also individual object instances. And so here we can try to develop a similar inspired approach for instance segmentation, where we're combining together these kind of multimodal signals with 2D color input as well as the 3D geometry. And again, we take a similar kind of feature extraction approach of semantic feature extraction from the color images that is also spatially downsampling, and then projecting both into 3D. And now for instance segmentation, we have a region proposal where we use both a set of small anchors and a set of large anchors, since in 3D we do actually have knowledge of scale. So we can separate objects into small objects and large objects, and basically have the anchor prediction based on the receptive field size of the prediction. So basically, you know, large anchors will have larger receptive field size than the small anchors at this point in time. And then from the region proposal and extraction, we can then predict object instance masks. So here we have the final kind of output prediction, which is basically the detected object box, and from within that, the instance segmentation mask. And so we can see a similar kind of trend here for instance segmentation in terms of how we combine together color and geometry. So when we use color only or geometry only, we get a similar-ish kind of performance here. And when we combine them both together, there's actually a noticeable complementary jump in performance. in terms of the ability to detect and segment these individual object instances. And so here you can see the visual representation of this instance segmentation, where this allows us to more reliably get the object bounding boxes, their object masks, by combining together this kind of joint color and geometry information. And so I think that we can kind of take this one step further in terms of how to incorporate together color and geometry signal. And so these scans that you see here in terms of the reconstructions, they are like not full geometric representations of the actual scenes, right? So you can see these kind of holes in like typically occluded regions and stuff like this that don't actually represent the full geometry of a scene. So in fact, we can potentially help this kind of semantic task of instance segmentation by learning to predict actually the complete geometry for each object. And so here, this is this task where we want to be able to kind of like see behind the observations that have been made, right? So from a single image or even from a series of images, there are regions that you haven't seen and that are important for understanding the like complete object as well as that like semantic functionality of that particular object. So here the task is from a reconstructed RGBD scan. We want to detect all the object instances and also predict the complete geometry of every object instance in addition to the observed geometry. And so here we get a decomposition into objects and their complete shape geometry. So here we take a similar kind of approach from the beginning. We have these geometric features, we have the color features. Here I've simplified it now. It's this similar kind of spatial extraction, and then we have this 3D backbone in order to perform the feature extraction from both this joint color geometry learning. And we have, again, these small anchors and large anchors determined by receptive field size in order to get the object detection. And then we predict the object class label as well as their final geometries. And so here this is actually done end-to-end, which is important for this particular task because that means that when we predict the complete geometry, that does have the ability to backpropagate into the previous object detection, classification kind of components so that all three of them can be learned jointly together. So if the box is a bit too small, that can get a bit of signal from the object completion in terms of what the actual object box detection should look like. So here we can see some visual results of this particular approach on some real-world RGBD scans from ScanNet, where we have the input scan and then our predicted individual objects. So these are colored only by instances. So each individual instance is a different color. And their predicted complete geometry here. And so here, what is helpful is basically that a lot of objects end up looking geometrically relatively similar to each other, like all of these chairs or sofas in these scenes. But they might look quite different from each other because they've been seen from different views. And so predicting this kind of unified space in which the complete geometry actually looks more similar helps to inform the actual semantic understanding part of the problem here. And we can see this also quantitatively. So here we're analyzing a few different things. So first is like, what's the effect of doing this kind of end-to-end? And if we perform kind of scene completion, just geometrically speaking, we try to complete the scene. And then after that, on the scene completion, we run instance segmentation. So this is a decoupled approach to this particular task. Then the performance is not so good because you end up with these kind of error propagation from, not quite perfect geometric completion that ends up basically accumulating errors once you forward it through the second part of the pipeline of instance segmentation. And we can turn it around and do the other task as well in terms of first instance segmentation, we find these partial objects, and then for every kind of detected partial object, we want to perform an object completion. And that has also similar kinds of problems in terms of error propagation, in terms of like maybe the detected object box is not quite the right size, or the instance segmentation on this partial object is not the most robust, and then you end up forwarding that through to an object completion. So the performance is not the most reliable in either of these two cases, but when we learn this instance completion task end to end, then we can end up with the signal propagating back from the object completion also towards this kind of instance detection kind of task. And we can take a look also one step further in terms of how does this completion task affect instance segmentation performance. So here we have basically an instance segmentation approach, which is 3D SIS, the prior one. And then we can perform our basic backbone without any completion. And that gets us already a little bit more performance because the backbone is a little bit improved. But then when we actually add on the completion task itself, that actually helps as well with the instance segmentation performance. And so here it's really the hallucination of kind of complete object instances that helps to associate them together in this unified space that brings this kind of performance improvement here. And you can see also the numbers are not necessarily super high, so this is kind of like a place that I think would be an interesting start to improve on in terms of understanding from both a geometric and also from this like image-based perspective. And I think, so one particularly interesting aspect of all this kind of 2D, 3D kind of like interaction is that I think, you know, people have started to bring up in the research community the fact that, well, like us as humans, well, we do have the ability to perceive 3D since we have two eyes. We also have quite a bit of ability to perceive geometry and depth with only one of those eyes. So if you cover up one eye, you still have a reasonable 3D kind of perception approximation of the environment. So what can we do actually to perceive both this kind of 3D geometry and semantics from images only? And I think that that's an important task also in terms of really learning to kind of generalize towards new environments, is logistically in terms of sensors, and as well as really providing a 3D understanding that's underlying this kind of 2D input. So here what we're taking advantage of is the fact that we actually have made quite a bit of progress in terms of object understanding, and we have actually a lot of 3D assets of synthetic shapes. So here we have like, and this is not the data that we're using, but it would be nice. IKEA has like a massive catalog of 3D assets of their furniture, and they create all of the renderings in their catalog this way. And so we want to take this kind of inspiration to decompose the 2D image into a semantic understanding that's based on 3D synthetic objects. And so that has the advantage of a 3D kind of object already by nature being a complete kind of clean mesh model that we can actually decompose into this object-based understanding of the 3D from these 2D images. So of course we're not using the IKEA data set, we use other models similar to ShapeNet style. But the pipeline here you see is basically, it's based off of a traditional 2D instance segmentation approach, in this case ShapeMask, which is built upon RetinaNet for the object detection. And here we perform instance segmentation first in the 2D domain. And from these instance segmentation, the features for every individual object, we try to associate this kind of different domains of the 2D image views and the 3D shapes. And so we embed them into this kind of joint embedding space between images and shapes to be able to retrieve a similar CAD model that represents that particular object. And so what we want is not just the shape, but we also want the kind of object pose. So here we also regress the object centers as well as the rotation of the object with respect to the image view, so that we can actually create this final kind of object-based 3D understanding from this image. So in a bit more concrete detail, the 3D perception part of this pipeline is based on this image shape embedding, where basically the images are represented by the features extracted from the 2D segmentation, and the shapes are represented by many different rendered views of these shapes. So they lie in a similar kind of domain, and they're both being encoded. So learned with a contrastive loss in order to embed them into a similar domain where we have semantically similar kind of RGB input that is able to be correlated with the 3D shape itself. So that's important for this kind of interaction between the two different kind of domains. And then we predict the object pose as its center and its rotation, where the center is predicted by a Huber loss, and the pose is predicted by first classification of the pose and then regression of the refinement offset of that particular pose. And that lets us get to this kind of CAD-based representation of every object in a scene, where we already know, since it's a CAD model representation, that it's like a relatively clean, complete representation of that 3D geometry. And so we can train and evaluate this kind of approach on the Pix3D dataset, which has a very accurate kind of correspondence of 3D CAD models to images. And here, this is in comparison to MESR-CNN, which also showed a pretty impressive 3D understanding based on generative model to create a mesh for every single object instance. And here we're evaluating basically the mesh AP. So how accurately that mesh is representing the ground truth 3D here. And this is based on this combination of retrieval as well as pose prediction to be able to get this more accurate prediction of the mesh AP. And you can see some of the visual results here in terms of, so here we have the input image and the predicted 3D representation of the objects as well as the ground truth. So this is representing basically the shape prediction as well as the pose prediction from this image view. And from here, we can get a pretty reliable shape prediction as well as the pose. So another kind of nice advantage of using this CAD-based, retrieval-based kind of approach is that you know, we have an available data set of CAD models, but in fact, if we get more, we can actually add them to the data set for retrieval. And so here we can actually add in, again, more CAD models that might be available at test time. And we see that, like, our approach, even though has not been trained on these particular CAD models, can still embed them effectively into this image shape space, as well as predict the reasonable poses in order to get actually a performance improvement by adding in more CAD models now into the candidate set for retrieval. So I think this is a pretty nice property in terms of leveraging this CAD-based representation here. And one thing that is important to note is that this particular Pix3D dataset does have quite impressive alignment between 3D CAD models and images, and often, like, I think this is because they are largely based on IKEA furniture kind of models, but often in the real world, you don't really have these kind of perfect one-to-one alignments between your CAD model data set and the real world images that you've observed. And so we also want to kind of see how this can work with real world images that don't have perfect correspondence. So here we're taking a look at the scanned tag data set, which is basically ScanNet images from RGBD video. You can kind of see that because there's a lot of image blur in some of these images, and ShapeNet CAD models that are associated with the 3D of these particular scenes. And so here the ShapeNet models are not a perfect one-to-one correspondence, but they are geometrically and semantically relatively similar as from human annotations. And so here actually you can see that in this particular case where we have actually quite a lot more objects, as well as this not kind of one-to-one scenario, we're also able to perform quite a bit of recognition as well as post-optimization for the objects here to understand actually these objects in these relatively cluttered complex scenes. So I think this is an interesting kind of way to represent the semantics as well as the 3D of these particular scenes to understand them from image observations. And that's also gives a lot of potential in terms of coming back a bit to more to this like localization task. You know, I think we would like to be able to enable like these semantic anchors, especially for long-term changes, where things might have actually moved around quite a bit, where we want to be able to recognize these kind of higher level features that aggregate together lower level geometric or color kind of information to combine it to a more object-based or even higher level kind of understanding, I think is a pretty interesting way to take a look at you know, 3D understanding, reconstruction, as well as this particular localization task. So with that, I would like to conclude. I'm also happy to take any questions.
Thank you very much for this great talk. We have time for questions, so if there's someone in the audience who would like to ask a question, please use the Q&A feature from Zoom to ask questions, and then we'll forward them to Angela. Similar if you're a panelist, so if you have a question, just feel free to unmute yourself and ask at any point in time. While people are typing in questions, I have a couple of them. So one thing that, I'm very impressed by the results of what you can get from 2D images and the CAD database, especially when it comes to the fine-grained structures. And I was wondering whether you can use the results you get to actually figure out what the variations in the real world instances of the CAD models are. Do you see a way to essentially refine your CAD database by saying, okay, I've seen this version of the model in the real world?
I mean, I think one thing that you're referring to that is pretty interesting kind of direction is basically these CAD models, because they're never really truly representing the distribution that we see in the real world. Like, how can we kind of deform them or modify them or figure out actually what does actually represent these real world objects? And I think that's got a lot of also promise in this direction, because there's been a lot of impressive work in terms of deformation of meshes as well as just pure shape generation recently. In like the last couple of months, the field moves very fast. But to be able to kind of identify like which objects are actually similar, I think that goes back to some nice work that has been done, I think, originally in graphics and probably in vision quite some time ago, to identify, you know, what kind of similar attributes in terms of objects or object parts are actually reappearing, because that does happen a lot, especially in a similar kind of in an environment like a university or even a house, or you often have the same object actually appearing multiple times. And I think that that's actually something that is an interesting kind of prior that would be nice to be able to learn, or to even incorporate directly, like basically to identify you know, what objects might actually be the same in an image or some kind of observation of a scene, because then you could also kind of unify these partial observations of, like, the different chairs, because chances are actually the same particular chair, just in many different instances and observations. I think that's a good way to further this kind of like scene understanding.
Thank you. And well, so again, a call to the audience, please use the Q&A button to ask questions. But I actually have some more that we could start with. So you saw that you see a diminishing return in using more views when it came to combining 2D and 3D semantics. Is this an issue of you have mostly images from the same viewpoint, or like there's not enough viewpoint variation in there, or?
It's largely an issue of, I mean, similar to what you said, but in terms of coverage. So there's an issue in terms of the data set being limited at some point in terms of the amount of coverage, because usually it's not full coverage over any particular point in the scene. But it is also that basically, depending on the field of view of your camera, like you can cover most of an object with, let's say, like three or four views. Then you'll have seen most of that particular object. And so the information becomes less informative, or it becomes a bit redundant. I don't think it becomes, like, it doesn't really detract from the understanding of that particular object, but you will have seen most of it at this point, and so that's kind of contributing towards these diminishing returns. But it would be interesting in this regard to kind of be able to figure out which views or which parts are actually the most informative towards recognition, because there's certainly, like, some views are easier to recognize, at least for people, like in objects, than other views, especially if they're deviating significantly from this kind of canonical understanding of the object. That would be also a pretty interesting thing to take a look at.
I was actually wondering in this direction whether the instance level completion could help you, in the sense of that, given the views that you have, you get the completion, and you could potentially figure out whether you're already sure that this is the actual shape, or whether you would need additional views to resolve ambiguities.
Yeah, I think in terms of the uncertainty kind of estimation part, this is kind of interesting in terms of how different of the predictions will you make actually from different particular views. Of course, it's a bit difficult to decouple that from the training of the generative model itself. Like if it overfits a lot, it will probably predict the same stuff for a lot of different kind of views. So it does need to be decoupled to some degree from that. But I think it's also important in terms of the completion task, generally speaking. If we move a little bit further away from these RGBD scan type scenarios where you have actually seen most of the scene, to something where you've actually seen, from like a single image, but you want to actually generate most of the scene, then we need to have a better understanding of the uncertainty of the different modes to be able to have a better generative model. So this is a bit of a chicken and egg kind of problem. To be able to actually have a good generative model, I think you need to actually have a good estimation within that particular model of how certain the predictions might be. And if they're relatively uncertain, then we should be able to predict multiple modes of what the possibilities are. But in the same kind of line, maybe it's also helpful to hallucinate these kinds of different modes of what the scene geometry is directly for these kinds of localization tasks, because that's maybe providing you a more reliable feature matching across very different kind of views of an object, if you can unify it into a canonical space where things match a little bit better. That's also, I think, an interesting direction that some people have also started to explore.
Thanks. And maybe one final question, when going back to the lifting 2D images to 3D. Have you thought of using single view depth prediction as some sort of core signal to help there, or?
Yeah, definitely. It's an interesting challenge, I think, at this point of single image 3D understanding that I think not many people have taken a look at, and also I kind of glossed over in this particular talk, is that it's difficult to evaluate, I think, what is a reasonable prediction actually of the 3D understanding, because you can obviously measure a direct accuracy of the 3D representation, but it might be that you know, you have actually what looks like a very plausible reconstruction, but it's just shifted off by 10 or 20 centimeters or something like this, which is, you know, I think the state of the art RGB to depth prediction is still around 20 centimeters-ish. So like, that is something, if you went by human perception, I think people largely don't estimate very precise, accurate kind of depth. It's something that seems to be a bit more coarse than that. So it's kind of interesting to balance these two kinds of things. But what does help in terms of the single image depth prediction, and this is something that we're also taking a look at, is seeding kind of the 3D understanding based on this estimate of the depth. Because I think what is really beneficial here is when you do single image depth prediction, you do need to generalize over a large variety of image views. And that does help you reduce significantly the depth ambiguity of objects. Because of course, like, you know, the object can be at any depth along the ray, just at different kind of scales. And that's something that's difficult to disambiguate, especially with more limited data sets when we have explicit supervision from 3D CAD models that are associated with images. It helps a lot to have this kind of more general understanding of RGB to depth. And what might be even more accurate is if you kind of allow for more than one image, then you can actually potentially perform a real triangulation process with multiple images to get a much more reliable prediction.
Okay, thank you very much. There don't seem to be any questions from the audience. So thank you very much for the great talk. I very much enjoyed it.
Thanks for having me.
Our pleasure.